Okay, let's see here. And we're recording. Okay, good. So here we are where we were last time. Reminder of what we were talking about. We were talking about how to use the chain rule if you're taking second partials. And so just as a reminder, again, we had this scenario where this was our diagram of variables. Again, I'm a big believer in making your diagram of variables. Sometimes I call it the road map, right? This allows you to keep track of where you are and where you came from and what's in between and that sort of thing. So first derivative, partial with respect to r, is just straight up doing the chain rule. We talked through that last time. And then now let me point out again, it's very helpful to have this roadmap in place, because as I take the second partial with respect to r, I can see very conveniently that means that theta is going to be a constant. That's what partial derivatives are, and I see that theta specifically is the one that's going to be a constant because it's in the same sort of group, right, of variables as r. So, well, if theta is a constant, then cosine of theta is a constant, and constants, you can pull this move that y'all all remember from single variable calculus, I'm sure. And I think this is about where we ran out of time. Okay. All right. So the big idea here is, let's see here. Oh, I need to zoom back. I'm sorry. By the way, you may have noticed I'm using a new PDF annotator today. It's a little bit more powerful. It allows me to do some cool things. I can do the finger pinching thing now that I couldn't do before. So anyway, looking at our scenario, let's talk about how to compute this thing. The partial derivative of this thing, zx. And what I did spend some time on last time was pointing out that viewing this as, can I perhaps view that as being z xr? Is this a reasonable notation? And it's really not, right? Because x and r are not inputs to a function with z being the output that I can talk about taking a partial derivative of. X and r are importantly at different levels. X is a function of r, among other things. So this just doesn't make any sense. That's catastrophically meaningless, really. So what we have to do is figure out how are we going to make sense out of this. And the big idea that I may have talked through last time, I don't remember, but the big idea is that if z is a function of x and y, then what can I say about zx? Well, zx is also a function of x and y, and let's include it correspondingly on the diagram. The diagram is how we keep track of stuff. It's how we keep track of what's a function of what and what's in between and what's an intermediate variable, and having it on the diagram is very helpful toward that end. So there it is. I'm going to put zx there on the diagram, and likewise, analogously, zy. I'm going to need to take its partial with respect to r. How am I going to do that? I need to understand where it is on the diagram. Well, likewise, it too is a function of x and y. So now with this appended diagram, trying to make sense out of the partial of, let's see here, let me get my colors straight, the partial of zx, there it is, with respect to r, there it is, no sweat. There's two intermediate variables, x and y. And so this partial derivative that I'm interested in has two terms corresponding to the two intermediate variables. Nothing to it. If you've been diligent and careful about having your diagram accurately document what's a function of what and what's in between, and again, if you have a good roadmap that you where you represent everything that you really need to. Everybody on board? Okay. All right. It's all downhill from here. That's the tricky curve. This is the tricky bit. Just to be clear, make sure that you keep your diagram up to date. And then notice, again, throughout this entire solution, slowly and carefully, right? Don't try to jump over and do 3 steps all at once in your head. It's too much to keep track of. There's too many little delicacies that you have to worry about, right? So slowly and carefully here. Now, a very analogous argument can be made concerning, let's see here, where am I? This partial derivative, partial of zy with respect to r. Well, again, there's zy, there's r. There's two intermediate variables, x and y. So you get two terms in your partial derivative from the chain rule, and there are those two terms. Is that a hand or no? Oh, okay, yeah, that's all right. No, that's okay. That's a check-in. Yeah. Okay, so that observed. Like I say, it's all downhill from here. Partial of zx with respect to x. We have an existing notation for that. That's the second partial. We write it as zxx, for example. You could also, make it second partial of z with respect to x squared. That notation as well. But I think this one's a little bit more convenient and compact in this case. Let's see here. Partial of x with respect to r. Again, we already know the formula for x as a function of r. It's polar coordinates. X is r cosine theta. It's an easy partial derivative. And then et cetera on down the line, you can kind of group things together and move things around, and it simplifies very nicely as this. Everybody okay with that? Slowly and carefully. Big point on this. Yes?
This is like a little bit like further back, but can you explain one more time how you got the cosine theta and sine theta to begin with?
Yeah, sure. So the point here is, let's see here, that r and theta are the usual polar coordinates, which means, among other things, that x is r cosine theta. Okay. Right? And so the partial with respect to r, if this is what your x is, right, then taking the partial with respect to r is just straight up cosine theta. Yeah. Yep. Okay, now I want to show you all a neat application of this. Just happens to be exactly the tool that we need to do what I think is actually a really slick move. Now I saw this in a physics course, but again, those of you who are engineers probably see something like this in an engineering course. But the big tool that makes it all work is a math idea. So it's about this thing called the Laplacian operator. The Laplacian operator is represented with a triangle, kind of like the gradient notation, except upside down. Right? So do be careful about that. They are not interchangeable, and you can't use one to represent the other, and it's a very important difference. Okay, so that said, the Laplacian operator is huge in physics and therefore in engineering. It describes how, among other things, how waves flow, how heat moves, etc. Right? So very important thing. Now, what I've got here is a formula for the Laplacian, and you'll notice that my formula is, I'm going to say, in rectangular coordinates because the partials are with respect to rectangular variables. This makes sense if your function is written in rectangular coordinates, as, well, of course, very often is the case. But sometimes, such as in the example I'm about to show you, f might instead be written in spherical coordinates. And if you want to write this Laplacian, but you want to write it sort of using partials with respect to spherical coordinates, then this is the formula for the Laplacian. And I'm not going to go through the details to show you how to get there, but I'm going to point you in the right direction. And by the way, very often I give you all sort of a suggested exercise, work out these details, it'd be good practice, etc. I'm not suggesting this one. The tedium involved in cranking this all out is a lot, right? And but I do want you to understand how to get there, even if you don't actually do it. And the idea is you can just look at this expression here one bit at a time. So, for example, second partial of f with respect to theta. Well, there's f, there's theta. Right? F, after all, is a function of rectangular coordinates. Rectangular coordinates are functions of spherical coordinates in the usual way. just like the setup we had on the previous page, by the way. Right? It's just spherical instead of polar, morally equivalent. And how do you compute the second partial? Well, it's just like what we did on the previous page. You're going to talk about the partial of f with respect to x as being another sort of variable in this picture. You're going to append your diagram and use the chain rule a few times. And everything will work out, and you can compute what this thing here, the second partial with respect to theta, you can compute what that is. And then you can multiply it by 1 over rho squared sine squared phi. And then you can add what you get when you compute all the rest of these things, and you can see where the tedium comes in, right? It's a lot. But if you crank all of that out, what you will find is that you get that exactly, right? And so this great big monstrosity here on the page, they call this the spherical Laplacian, because it computes the exact same thing that this does, just in spherical coordinates. Now, what you're seeing here might be dissuading you from ever wanting to do such a thing. Why would I ever want to use a spherical Laplacian when, my gosh, look at it, the rectangular Laplacian looks so much nicer? Right? All right, we'll hold that thought. Let's consider how we use Laplacians. And here's an example. Let's talk about, so for example, gravitational potentials. This could just as well be electric potentials. By the way, it turns out gravitational fields and electric fields are structurally kind of identical. We'll talk more about that later in the course, but they're very, very similar, and mathematically they behave almost exactly the same ways. So take your pick, electric or gravitational. But what we call a gravitational potential has to satisfy this equation. This is called Laplace's equation. So the Laplacian has to be 0, as it turns out. So how would we find a solution to this? Well, we need to find some function that when I put it in here makes the equation work, and it turns out that this is a solution. Now, we're gonna talk about how to confirm that in just a moment. But I claim that this does end up being a solution. Now, how would we confirm it? Well, one thing you could do, if you wanted, is you could take your rectangular Laplacian, and you could take your rectangular formula for the function, and you could just crank it out, right? Apply that rectangular Laplacian to that rectangular formula for f, and take a deep breath and plow forward, keep your head down, right? Just go. And you can do that. And by the way, it's not even as bad as it looks. This will take you, look, I've done this a million times. I could probably crank that out in 5 minutes. But at first time through, it'd probably take you 20 minutes or something like that. Which is just kind of tedious, right? And all else being equal, I don't really want to do that if we can avoid it, right? Seem believable? You can kind of see it coming because as you, for example, let's take the x partial of this expression. It's a fraction. We're going to have to use the quotient rule. And in the denominator, we've got a chain rule problem. And worse, it's a chain rule where one of the functions is a square root, which means that we're going to have fractional exponents, and it's just annoying. Anyway. Can't remember if I said this yet, but everyone should do this once in their lives, and your time is coming. I forget exactly which section this is going to be a homework exercise, but you do need to crank through that. Like I say, it's a healthy classical calculation. All right, now here's your other alternative. Your other alternative would be to use the spherical Laplacian applied to the spherical formula for our candidate function, right? Instead of doing this, what I had in green there, we could do everything in spherical coordinates. Spherical Laplacian, spherical candidate function, and we could crank this out. let's see here, highlighting again. And you might be thinking, oh my God, that's so much worse, right? Look at all the brutal on there, right? That's a lot of ugly. We're going to do this calculation right now, and we're not even going to have to write anything down. That's how easy this calculus. This is a falling down, simple calculation, and here it comes. I love how wonderfully, conveniently this works out. Okay, step one. Let's apply this partial to that function. Oh, there's no thetas in here. That's 0. This whole thing is gone. Everybody see how that worked? Right? The very moment you say, I need to take a theta partial of this thing that has no thetas in it, we're done here. So that term disappears. Next, how about let's look at this great big, that's scary looking, until you realize that I'm going to be taking a phi partial of something that has no phis in it. Now that term is gone too. Again, I still haven't really had to write anything down. Terms just keep disappearing. It's awesome. Everybody with me? Dig. Okay, third one. Here we are going to have to kind of think about things a little bit, but it works out really nicely. Let's start by taking the rho partial of this. Well, it does have a rho in it. The rho partial of constant over rho is going to have a 1 over rho squared factor in there. Now, I point out then that 1 over rho squared, you multiply by this rho squared, and in fact, then this right here is a constant. What is it, like minus k or something? Yeah? Oh, okay. Constant. And then let's see, now I need to take a partial with respect to rho of a constant. 0, again, and we're done. Right? Hardly any effort at all. No nasty quotient rule or various forms of ugliness that you would have seen, that you will soon see when you go through this calculation rectangularly. Right? Just boom. Pretty awesome. So you have to pay careful attention to when you are thinking about how to approach one of these calculations in your future engineering lives or physics lives or what have you. And if the computation you're looking at might be able to be rewritten, right? If that could conceivably be written in a way that's clearly simpler, it's worth entertaining the possibility that maybe that's how you should do it. All right. So again, all of this, this wonderfully powerful method here for dealing with this very natural physics problem of gravitational potentials and whether they do or don't behave as they should, comes about because of the formula we have for the spherical Laplacian, which comes about because we know how to, for example, take second partials using the chain rule. Right, so that's one of the reasons why all this stuff here on the previous page is really important. It's this is an example of the kind of stuff that leads to these powerful results. Yeah.
So understanding that in context, like just how it's 0, does that just mean no? I know that's like more physics, but is there a way to interpret that?
It's not as easy as. It would take some time, and it's, I'm going to say not a good use of class time. There is an answer, but it's not a quick one. Okay. Yeah. The motivations for, various formulas that we write down that describe different physical phenomena are there's always a reason that they write it down, and it's always ultimately natural and simple, but sometimes, such as in this case, it takes a little bit of careful thinking through. All right, so moving along. So, new idea called directional derivatives. I want to motivate this in a way that's maybe a little different. You'll notice what I've started with is a summary of facts about partial derivatives. And I'll remind you that partial derivatives have the following interpretations. Partial derivatives can be thought of as a slope of the graph, details to follow, of course. It's a multiplicative factor, interpreted appropriately, of course. We didn't ever write this down before, but this expression right here, if you look at it carefully, what we have on the inside here, actually, let me do my cool new zoom. See if I can, there we go. Okay, so this expression right here, this says I'm at the point A and moving with velocity EI. In other words, this in here describes a scenario of being at a certain location and moving in a certain direction. And when I'm in the domain at this point and moving in that direction, this just says how fast is the function changing. So this expression that I've got written here, again, we haven't written down before, but it just pretty directly tells us this idea that partial derivatives keep track of how the function is changing as you move in the direction of a given variable. So I'm going to say this makes sense in terms of one of our previous interpretations of partial derivatives. And then we have also previously seen this expression right here. Might not look like it, but gradient is a vector whose coordinates are the various partial derivatives, and EI is a vector that's all zeros, except for a single one in a particular position, and so when you do that dot product, you literally get that partial derivative. Okay, so summarizing, all four of these things are equal to each other. If you're talking about moving in the direction of a particular coordinate, that's and of course the direction described by for a particular coordinate is described by its standard basis vector. Okay, now next observation I want to make. Let's not think about the fact that these four things are all equal to a partial derivative. Let's think about the fact that these four things are all equal to each other. And whether we call it a partial derivative, I'm going to set that aside for the moment. These four things are all equal to each other. Is that cool? So I ask now, rhetorically, does it really matter that we're moving in the direction of a coordinate axis? For these four things all to be equal to each other, does this only work if we're looking along a coordinate axis? And the reason I'm talking about it in that way is I want to point out that coordinates kind of don't matter here. Coordinates are kind of arbitrary. For example, let's talk about the temperature in this room, right, which I think is a little high, by the way. Anyway, if you want to flip it, yeah, that'd be great. Yeah, thank you. Yeah. So the temperature in this room, right? And I could talk about the temperature here, and I could, at this point, I could set up an axis system, and there's a natural inclination to want to make your axes parallel to the walls and floor, etc. But you don't have to. All right, I could just as well say, okay, I'm going to use this as my coordinate system, right? And so that's going to be my x1, and there's x2, and there's x3, and that still works, right? And now, basically the idea then is that any vector, any unit vector at all could be a standard basis vector if you set up your coordinate system that way. Temperature in this room isn't really a function of coordinates. Deep down, temperature in this room is a function of where are you, right? Literally physical, actual location. Coordinates are kind of an illusion. They're sort of a tool that we use that's convenient in certain circumstances, but ultimately they're just kind of this imaginary thing that we make up for convenience. So if this coincidence, these four things being all equal to each other, only works if you're talking about a vector pointing, unit vector pointing in the direction of an axis, well, any vector could be a vector pointing in the direction of an axis. So these four things that I have highlighted should still all equal to each other no matter what unit vector I'm using. Because, again, just choose your coordinate system, however is most convenient. You buy it? Okay. All right, so that noted. By the way, this is 100% true. And these four things are still equal to each other. This expression and that expression, same exact expressions I had above, slope of the graph, factor that you multiply, these four things are all equal to each other no matter which direction you're looking in. Now, the reality is, coordinates are convenient sometimes, and typically we do pick a coordinate system. And so the vector that I'm using here, I can't say that, even though it could have been a standard basis vector, probably isn't. So I can't call this a partial derivative, right? I have to think of a new name for it, for this vector that's playing the role of a standard basis vector. So yeah, got to think up a new name. But it remains that these four things are still all equal to each other. These natural connections are still there. So here's the new name. We call this a directional derivative. And when you see directional derivative, what I encourage you to think in your head is, it's like a partial, morally the same as a partial derivative. It's just sort of in a different direction than a standard basis vector direction. Here's the notation. D for, I have to admit, I'm not sure, is that a D for directional or a D for derivative? Could be either, I suppose. But the big D, subscript to indicate what direction are we talking about. So the V, right, whatever vector we're using here, that has to be a subscript. Of course, you have to indicate what function you're talking about taking a directional derivative of, and of course you have to indicate where, at which point are you computing that directional derivative. So that's the notation. The big idea is whatever the direction is, that's your subscript. Everything else is pretty routine. Okay. In fact, why don't I go ahead and highlight that as well. So, there you go. This is what a directional derivative is. It's a rip-off of the idea of a partial derivative applied in any other unit vector direction. Really nice. We all of a sudden instantly know tons of things about directional derivative. Directional derivatives can be computed with this handy-dandy formula. Directional derivatives can be interpreted as giving you the slope of the graph as you move in that particular direction. And then here I'll point out that, as you move, looking at the picture down here, in the direction of whatever this vector is, that unit vector V, in that direction, you can look at a cross-section. You can talk about the slope of the graph. The directional derivative will compute that for you. And it's also this multiplicative factor. Now, I want to talk about the multiplicative factor real quick because there's a nice notation associated with this. If we're talking about the directional derivative as being this multiplicative factor, if it's what you multiply by your input change, either how far have you moved in that direction or how fast are you moving in that direction, and if the result is your output change, again, either how much did the output change or how fast is the output changing, what would make sense given this context, that given that the directional derivative is the thing I multiply by these green things to get those blue things, doesn't it make sense just notationally that we should write the directional derivative in this case as df/ds, sometimes pronounced rate of change with respect to distance. So I emphasize, not the same as rate of change with respect to time. Rate of change with respect to time depends on how fast you're going. Right? But rate of change with respect to distance is, just doesn't depend on time, doesn't depend on how fast you're moving. It's just for every foot that you go that way, how much does the function increase? Is that cool? A little metaphor for this is to distinguish between what I like to call the road versus the road trip. All right, so let's suppose we're taking a drive through the mountains, right? We could talk about, as I drive along the road, how fast is my altitude changing? And how fast my altitude is changing means, rate of change with respect to time. I'm looking at my altimeter, and I want to see how fast my altitude is changing. How many feet per second is my altitude increasing? DFDS says, I don't really care about your personal experience. It just says, how much does the altitude change per distance traveled along the road? How steep is the road? It's got nothing to do with you. It's all about the road. Does that make sense to everybody? So you want to distinguish between the road and the road trip, right? DFDS, directional derivatives, are about the road. Time derivatives are about the road trip. All right. Okay, so all that in mind, here we go. Let's see here. There we go. So here's an example. I've got some function. The question asks, what's the slope of the graph at a particular point and in a certain direction? Okay, well, this is just right down the pipe, exactly an application of directional derivatives, because that's what directional derivatives compute, among other things. This is one thing that I can say is, slope of the graph. That is on the list of interpretations for directional derivatives. How do we compute directional derivative? Well, on the previous page, we have a formula that says you compute directional derivatives with, you've got options, but the easiest one to use most of the time, dot product with the gradient. Everybody good? And then it's kind of all over at this point. The gradient, compute the appropriate partials, plug in the appropriate point. There it is. Now, there is a little tricky bit here, and you do have to be careful with this. The vector that I'm using here does have to be a unit vector. Remember, the idea is the vector it needs to be what could have been a standard basis vector had I set up my coordinate system appropriately. So, has to be a unit vector. So, it has to be the unit vector pointing in the direction of the vector that I'm using to describe what direction I'm going, right? So don't forget to divide your direction vector by its magnitude to get your actual unit vector. And again, that's just a matter of writing it down. And so our answer, the slope we were looking for, is this dot product, which is arithmetic. And directional derivative crushed this problem for us. Is everybody happy? Okay. Now I want to talk about terminology a little bit. This is a common misunderstanding. It says here, in the direction of a vector. Let me draw a little picture over here. So I'm at the point 3, 1. Let's see here. Here we go. I'm at this point 3, 1. And it says in the direction of the vector 3, 4. Okay, now I need to draw a 3, 4. Very importantly, a vector, not a point. For one thing, it says vector. Right there. Right? For another thing, it says the direction of. Points don't have directions. Right? Points have locations. This doesn't say toward the location 3, 4, right? It says in the direction of 3, 4, that means interpreting 3, 4 as having a direction. That means 3, 4 is a vector. So that vector, 3, 4, is about like that. So again, make sure you interpret this correctly. Some students get confused and they see a 3, 4 and they think, oh, well, 3, 4 is a point. It's a point that's about right there. And this question must mean that I'm going toward the point 3, 4. Very importantly, not what the question is asking, right? So we are not talking about that way. We're talking about that way. Everybody see the difference? You got to pay real careful attention to the phrasing in situations like this and make sure you interpret the question correct. In proper interpretation of the language is part of the question in some sense. Everybody happy? Okay, cool. I use another example. This is another sort of immediate application, and notice here the question says to compute dTdS. Okay, well, dTdS, directional derivative. Again, right down the pipe. One of our listed interpretations of directional derivative. Rate of change with respect to distance. Cool. And again, pat formula for how to compute directional derivatives. Dot product with the gradient. So you compute the gradient, you dot with the unit vector, boom, answer. Everything else is details. Is everybody happy with the how I connected this to this calculation? Follows. All right, now I have some bad news. Oh gosh, depending on who you talk to, there are different interpretations of the word directional derivative. This is a source of great frustration for me, anyway. Now you'll notice I very specifically here, and I want to highlight to emphasize, very specifically, I have defined directional derivative only where this is a unit vector. It's got to be a unit vector. The argument that I made here to get all the interpretations to kind of come along, to be able to steal, right, borrow all of those interpretations from partial derivatives, I had to make this a unit vector. Some people like to point out that I don't need all those interpretations. Maybe I just want some of those interpretations. And very often I find myself, look, I'm at a certain point and I'm moving with a certain velocity. I want to be able to talk about how fast the function's changing, and they like the term directional derivative. So in some contexts, they'll use the term directional derivative even when it's not a unit vector. And so you get a different thing. Right? Now, in particular, I want to point out exactly what works and exactly what doesn't. If you remove this condition, if you no longer require that the vector be a unit vector, it remains that this thing is still computed by that formula, it is still computed by that formula, so all of this still good. No problem. What you lose is you can no longer interpret your result as being a slope, and you can no longer interpret what you've got as being a multiplicative factor. And so you can no longer write it as df ds, right? So all of that goes out the window. But it remains that how fast the function is changing is computed by a handy-dandy little formula, and again, really useful in a lot of circumstances. So not only are there some, but I would say that there are many mathematicians that subscribe to this point of view, right? That maybe we shouldn't have such a requirement. And then you interpret accordingly. In fact, I think it's fair to say that I don't want to overstate it, right? But in some sense, most mathematicians, actually make this interpretation I myself. Outside of the context of this course, this is my preferred interpretation. But we are in a course taught by use of our particular chosen textbook. In our chosen textbook, they insist on that unitness, and it would be way too confusing to have the book have one definition and for the course to make a significantly different definition. We just can't have that. So despite my personal preferences, in Math219, this is purely a cultural point. Right? In Math219, we are sticking with the previously given definition, which I will recover here. We will continue to require all of these. We'll continue to require that be a unit vector, and colors, and all of these still work. So in Math219 and this, in Math219, this is what directional derivative shall mean. Is that cool? Just heads up out there, outside of this course, there's this nasty problem of, you hear someone say the word directional derivative. Is he one of those other guys that doesn't require it to be a unit vector, or is he a Math219 kind of person that does insist that it be a unit vector? And so I mention this because you just need to always be heads up, right? It's another little sort of cultural landmine that if you aren't careful, you'll accidentally misinterpret what someone's telling you. So, annoying situation, but it's it is what it is. Okay, let's talk about this question. Here's a natural question to ask. Let's talk about our directional derivative. How fast the function is changing. Directional derivative, of course, defined for unit vectors, v. So we want to entertain all possible unit vectors. And the question is, we're going to try to figure out which one of these directions, of all these possible directions that I could be moving from there, right? Of all of them, which one makes the directional derivative as big as possible? I say it's a natural question because, for example, if I'm cold, right? I'm out there in the woods and I'm cold. I want to walk whichever direction is going to make the temperature increase as fast as possible, right? Toward the fire. Right? I don't want to walk in some random direction where the temperature is slowly increasing. I want every step I take to give me maximum possible warmth per step. Right? Does that make sense? Okay. Plenty of other scenarios, of course, where you want to know which direction makes your function increase as fast as possible. Now, do keep in mind that how fast the function is increasing, right, being one of our interpretations of the directional derivative. This direction that makes that increase as fast as possible, I think it's pretty reasonable to call that the direction of fastest increase, because it's the direction that makes the rate of increase as fast as possible. The terminology is just kind of, it builds itself, right? This obvious choice of words. On the other hand, now here's a different interpretation of directional derivative, right? Alternative interpretation, directional derivative is slope. So what words would I use to describe whichever vector it is that makes the slope of the graph as high as possible? And the common choice there is to call it the direction of steepest ascent. This, if it's making the slope the greatest, then it's the direction that's the steepest as you go in that direction. So another common terminology. Now, I have a personal feeling on the choice. between these two terms, right? The vector in question can be described by either one of these. If you think about it, this one about steepest ascent only makes sense if you're talking about graphs, because directional derivatives are slopes only if you're talking about graphs. This term here, direction of fastest increase, makes sense no matter what kind of picture you're looking at. It's literally, I want to make the function increase as fast as possible. Interpret the function however you want. Draw the picture however you want. Doesn't matter. Right? So this first expression is the more general. The second expression is more specific. You can probably guess. I have a preference for this top term here, direction of fastest increase. And anyway, sadly, the rest of the world seems to prefer this one, direction of steepest ascent. So you're going to hear this phrase, direction of steepest ascent, regularly, right? And what they mean is if you're looking at a graph, aka what they mean is direction of fastest increase. Is everybody clear on the terminology? Okay. So you're going to hear me say the first one. You're going to hear everyone else say the second one. How to compute it. What direction is this? Which of these many vectors is the right vector? Well, here's the argument. This is what I want to maximize. I want to make that as big as possible. It's computed by that formula, which you see as a dot product. Dot products are computed by that formula. All of my vectors are unit vectors, and so this magnitude right here, magnitude of v, is 1. So the thing that I want to maximize is that expression. That's what I want to try to make as big as possible. And if you think about it, this right here, the magnitude of the gradient, is a great big constant. I haven't moved, right? I'm still at this point A. I'm looking in different directions, but I haven't actually moved yet. That means the gradient is what it is. It's just sitting there. As I contemplate the various directions that I might go, I'm still at the same point that still has the same gradient. Okay, so now, how do I make this expression as big as possible? And this turns into a high school trig problem. I just want to make cosine theta as big as possible. And that's actually pretty easy. The biggest cosine theta can be as 1. And it happens when this angle, theta, right there, is 0. Is everybody on board? So theta equals 0, keeping in mind that theta is the angle between the vector I'm looking for and the gradient. It follows then that this vector v that I'm looking for, it's not over there. The vector v that I'm looking for is the unit vector in the direction of the gradient itself. And again, that's an easy formula. Unit vector in the direction of a given vector divided by the magnitude. Yeah? Nice fact. Handy little tool. You're going to find that there will be situations such as in homework exercises or on exams where the question's going to say, hey, here's a function. What's the direction of fastest increase? Right? Oh, okay. Well, boom. There you go. There's the answer. Just plug and chug. It's not even that much chug. Right? It's pretty easy. This is great news. There are questions that have really easy answers. Gotta love it when that happens. Okay, now how fast is the function increasing as you go in that direction, right? What is this optimal directional derivative? Well, again, calculation can allow us to come up with what the answer is. And the way we do this calculation is to recognize that we have a formula for our vector v. Our vector v is, there it is, it's gradient divided by the magnitude of the gradient. And then notice, as it turns out, conveniently, here I have gradient dot gradient. That's magnitude squared. And altogether, you have magnitude squared divided by magnitude, which gives you magnitude. So the maximum directional derivative, how steep is this hill, right? How steep is the graph? Magnitude of the gradient. So this summarizes really, really nicely. We just asked two very natural questions. What's the direction of fastest increase, and how fast is it increasing in that direction? And the direction of the gradient was the answer to the first question. The magnitude of the gradient was the answer to the second question. So this is a totally different point of view on gradients than y'all have seen before. Previously, the gradient, up to now, the gradient was an algebraic convenience. It was notational shorthand. It served to help us compute stuff. That's about it. Now, the gradient is a geometrically natural thing. Its direction is a natural direction. It points uphill. Its magnitude tells you steepness. Both of its geometric features are answers to natural questions. So this represents a big shift. And it looks like I'm out of time. So we'll draw the line right there. We'll pick up here on, don't forget, exam on Friday, right? So we'll pick up here on Monday. And, of course, all the stuff we did today, not fair game for the exam. Y'all saw my email the day before yesterday. Have a good one. See you later. And make sure you come talk to me if you didn't get marked down for attendance. Just a second here.